Let us further develop our discussion of functional approximations through this example. There is something called the error function denoted by this ERF of x. It's defined to be equal to 2 by square root of pi integral from 0 to x e to the power of minus psi squared d psi. That's what is given here. So if you are able to evaluate this integral from 0 to x and multiply it with 2 by root pi, you can get the value of the error function at the location x. We know that e to the power of minus psi squared can be represented as this infinite series about the point x is equal to 0. For example, you can look at the expansion of e to the power of x around x is equal to 0 as 1 plus x squared by 2 factorial plus x cubed by 3 factorial, etc. And if you're looking at e to the power of minus x, if you replace x by minus x in the expression above, you will get 1 minus x plus x squared by 2 factorial minus x cubed by 3 factorial plus and so on. So for e to the power of minus x, the sign of the terms keep alternating, whereas for e to the power of x, it is always plus sign. So that's the difference. So in this expression for e to the power of minus x, wherever I see x, I'm going to substitute by psi squared. So e to the power of minus psi squared will be equal to 1 minus psi squared plus psi squared squared. So psi to the power of 4 divided by 2 factorial minus psi to the power of 6 by 3 factorial plus minus and so on. I can represent the right hand side in compact form like this as what is given here. For example, if you take k is equal to 0, minus 1 to the power of 0 will be 1. Psi to the power of 2k when k is equal to 0 is going to be psi to the power of 0, which is equal to 1. And 0 factorial is 1. So 1 times 1 times 1 will be 1. Then for the next term, you get k is equal to 1. So minus 1 to the power of k. So minus 1 to the power of 1 is minus 1. So minus 1. Psi to the power of 2 times 1. So psi squared divided by 1 factorial, and 1 factorial is 1. Therefore, this is the second term. For the third term, k is equal to 2 and minus 1 to the power of 2 is 1. Psi to the power of 2 times 2 is 4. So plus psi to the power of 4. Then k factorial, k is 2, then you get 2 factorial and so on. So you can verify that what I wrote here is indeed correct and it can be represented in this compact form. So one way or the other, you must be convinced by now that I can write e to the power of minus psi squared as this. So ERF of x is going to be 2 by root pi integral 0 to x. So instead of e to the power of minus psi squared, I can replace by this right hand side. So it's going to be summation k is equal to 0 to infinity minus 1 to the power of k psi to the power of 2k by k factorial and d psi. Now this is easy to integrate term by term. Why? Because it is going to be a polynomial in psi, and integration of polynomials is easy. For example, integral of psi squared will be psi cubed by 3. Integral of psi to the power of 4 will be psi to the power of 5 by 5, etc. When I do that, I integrate term by term. The right hand side will become this. So when I proceed with this integration, I'm going to get 2 by root pi, then integral from 0 to x, 1 minus psi squared plus psi to the power of 4 by 2 factorial minus psi to the power of 6 by 3 factorial, etc. d psi. So it's going to be 2 by root pi. And if I take the first term, it is 1 times d psi. And if you integrate 1, you're going to get psi. And psi between the limits 0 to x will give you x. Now coming to the second term, you're going to get a minus sign from here. So I retain that minus sign. Psi squared d psi will be psi cubed by 3. And between the limits 0 to x, this is going to give x cubed by 3. And then it is going to be plus 1 by 2 factorial psi to the power of 4 d psi. When you integrate it, it is psi to the power of 5 by 5, and between the limit 0 to x, it is going to be x to the power of 5 by 5 minus and so on. So if you generalize, if you take a general term psi to the power of 2k by k factorial d psi, if you integrate a general term like this, you're going to get psi to the power of 2k plus 1 by 2k plus 1 between the limits 0 to x, and that is going to be multiplied by 1 by k factorial. That term will be there, so 1 by k factorial. So this is going to give us x to the power of 2k plus 1 by 2k plus 1 multiplied by k factorial, and that is indeed what you see here. This takes care of the alternating sign. When k is odd, you will get a minus sign for minus 1 to the power of k, and when k is even, you're going to get plus 1 for those terms. So you can see that this represented in a compact form is what is given in this particular slide. So I hope you understand how this becomes this expression of e to the power of minus psi squared as an infinite series. And then because this is going to be in terms of psi squared, psi to the power of 4, psi to the power of 6, etc. If you integrate it term by term, you will get the error function at x as the sum of an infinite series like this. And please note, the right hand side is a polynomial in x. Next, what we do is, instead of expressing ERF of x as the sum of an infinite series, I'm willing to take an approximation. I would like to go only from k is equal to 0 to n, and from k is equal to n plus 1 till k is equal to infinity, I'm just going to sum all of them up and put it in this term r of x. So this r of x is a residual. So I'm going to truncate it after k reaches n and say that's the value of the error function of x. I'm just going to say that this r of x is going to be very small. I don't have to go for the infinite series. I can stop it after a certain number of terms. So when k reaches n, the power of x will be x to the power of 2 times n plus 1. So the polynomial that I'm going to get in x, that polynomial will be of the order of 2n plus 1. So this will be a finite order polynomial approximation, whereas this was a infinite order polynomial equivalent. Now, as I said earlier, this r of x, which you have ignored, that's called the residual function, and the size of r of x represents what is called the truncation error, because we have truncated it after a certain number of terms. So this would be the truncation error. And the truncation error would depend on the value of x. This development was based on Taylor series expansion about x is equal to 0. So the further you stray away from x is equal to 0, the residual is going to be large. This approximation will be poor when x gets very large. When x is very close to 0, this approximation will be very good. When x is very different from 0, this approximation will be poor, which means this residual will get larger. As examples, you can see what happens when x is equal to 0.5. Let's try to evaluate ERF of 0.5. Now, if you just use n is equal to 2, that means you stop when k equals 2, the value that you get from this finite order polynomial approximation is 0.5207. The exact value is 0.5205. That means if you do the infinite series and you sum it up, you will get 0.5205 to be the exact answer for ERF of 0.5. But if you just stop with three terms, that means k is equal to 0, k is equal to 1, and k is equal to 2. So you just stop at n is equal to 2. You're considering k is equal to 0, k is equal to 1, and k is equal to 2. So three terms. So when you do that, you're going to get a value of 0.5207, which is quite good compared to the true value of 0.5205. And in fact, when you go to n is equal to 4, that means you have only 5 terms retained and the rest you throw away, you're going to get the exact value. So a small number of terms, if you retain in the finite order polynomial approximation, that is going to be good when x is equal to 0.5. Now, when you go away a little bit to x is equal to 1 and you're trying to find out ERF of 1, the true value is 0.842701, and you reach the true value at n is equal to 8. At n is equal to 2, 4, 6, the answers are quite approximate. But the moment you reach n is equal to 8, you're going to get values that are closer to the actual value. So as you move from x is equal to 0.5 to x is equal to 1, you suddenly require more terms to be retained in your finite order polynomial approximation. So this clearly shows that as you move away from 0, you will require more and more terms to be retained in your finite order polynomial approximation. And when x is equal to 2, further away from 0, what is going to happen is you're going to require n to be equal to 20 to reach the true value, which is 0.995322. So ERF of 2 is 0.995322. And you can reach that using a finite order polynomial approximation only when n is equal to 20. For smaller values of n, the answer is not as accurate, i.e., these approximations are valid around a certain operating point or around a certain reference point. If you go further away from your reference point, these approximations are going to have huge errors. So the same information is depicted in graphical form here. For example, when x is equal to 0.5, you get pretty good accuracy when n reaches a value of 5. What is shown on the vertical axis here is the error, the difference between the true value and your polynomial approximation. So the error comes to a value like 10 to the power of minus 6 or lower when n is equal to 5. When you're looking at x is equal to 1, you see that even with n is equal to 6 or 8 or 10, the error value is not as small as the error you see here for the case of x is equal to 0.5. And when x is equal to 2, the value of the error, even with n is equal to 10, is not as low as you get for x is equal to 1 or x is equal to 0.5. This is exactly the same trends we saw in the table in the previous slide. Now, if you come to this particular panel here, what you see is what happens at different values of x. When x is equal to 0, whether you have n is equal to 2, 4, 6 or 8, the error is 0. But if you have n is equal to 2, that means if you retain only 3 terms, that is n is equal to 2, the error grows very rapidly once you reach a value of x is equal to 0.5. But when you retain 9 terms in the expansion, that means when n is equal to 8, you see the approximation is very good until x is about 1.3, after which it takes off. So as you move away from x is equal to 0, you require to retain very large number of terms, or you have to use a large value of n in order to have errors to be as low as you would like it to be. All right, Taylor series expansion is a great idea, but we need to evaluate the derivatives. That means in order to express e to the power of x as 1 plus x squared by 2 factorial, etc., or e to the power of minus x as 1 minus x plus x squared by 2 factorial minus x cubed by 3 factorial, etc. And definitely for e to the power of minus psi squared, right? The expression that we wrote. For all of these expansions, Taylor series expansions, we need to evaluate the partial derivatives. For example, this you will get by using the first order derivative. This term you will get by using the second order derivative and evaluating the derivative at x is equal to 0 in this particular case, etc. So each term that you see on the right hand side in the Taylor series expansion requires the use of or evaluation of derivatives. That is cumbersome and sometimes very complex. And we also notice one thing. We will get into trouble with the approximation as you move away from the point around which the Taylor series expansion was obtained. So in our example earlier, as you move away from x is equal to 0, you're going to get into trouble. That means we require more and more terms to be retained in the model, etc. So the Taylor series expansion, even if you take the pain of evaluating the derivatives, etc., the accuracy will be lost as you move away from the point around which the Taylor series expansion was obtained. However, in engineering applications, we want to have functional approximations that are valid over a range of values. Let's say I want this function to be good from x is equal to a to x is equal to b. So how do we do that? So the key idea there is to work with what are called independent basis functions. And we can choose n of them. So they should be linearly independent as well. In linear algebra, this would be called as Li, linearly independent. We know linearly independent vectors. Likewise, you can have linearly independent functions. So you want to use basis functions, n of them, and when they are linearly independent, they are very efficient in spanning the space or in representing other functions. So that's the nice thing about having independent vectors or functions. Because if two functions are exactly linearly dependent, you're not going to be able to span that space well. You will span one direction. But to span the entire space, we would like linearly independent vectors, or when you're talking about functions, you would love to have linearly independent basis functions. So let's call those basis functions as psi I of x. So this is not fi of x, this should be psi I of x. And I goes from 1 to n because we are choosing n linearly independent basis functions. And you can construct these linearly independent basis functions. There are methods that help us to construct these functions over a range, given range, so that you can approximate the function f of x in terms of the basis functions. So what we can do is you can approximate f of x as a polynomial of order n, which can be represented as the sum of n basis functions. So this is going to be an idea which is like f of x can be approximated as a1 psi 1 of x plus a2 psi 2 of x all the way till an psi n of x. So you can represent it in this way. This is the key idea. Choose basis functions and you express the function in terms of a linear combination of those basis functions. You can choose as many basis functions as you want because this n is under your control. You can choose the value of n. The linearly independent basis functions psi I of x are to be carefully chosen. And you can determine the AIs, the coefficients, which are unknown at this stage using the idea of least squares. So that the functional approximation you construct is as close as possible to the function f of x. The tuning parameters for us are n. How many basis functions would you use? So that is one of the parameters that is under our choice. And once you have determined n, then you can determine the values of ai such that the error epsilon is as small as possible. Again, I said it's the idea of least squares. So we are looking at the true function minus the approximation. This is the functional approximation. This is the true function. This is its functional approximation. You want the gap between that to be as small as possible. So once you have fixed n, you can now use ai as the decision variables to make this gap between the true function and the functional approximation as small as possible. That's the idea. Now, one choice for our basis functions could be psi I of x is equal to x to the power of I minus 1. So my first basis function will be psi 1 of x, which will be x to the power of 1 minus 1, which is x to the power of 0, which is 1. My second basis function psi 2 of x would be x to the power of 2 minus 1, which is x to the power of 1, which is x. My third basis function would be x to the power of 3 minus 1, which will be x squared, and so on. So 1, x, x squared, x cubed, etc. could be the family of basis functions. If I choose this, then a polynomial of order n minus 1 can be constructed by choosing my phi of x, the basis functions, to be x to the power of I minus 1. So a1 psi 1 of x, so a1 times 1, plus a2 times psi 2 of x, so a2 times x, plus a3 times psi 3 of x, so a3 times x squared, and so on. And when you come to I is equal to n, you're going to get a n x to the power of n minus 1. So when you go from I is equal to 1 to n, using this choice of basis functions, we are going to get the functional approximation to be this. You can readily see that this would be a polynomial of order n minus 1. So this would be Pn minus 1, and that's what you see here. Let's say for a particular system, data is available for these values of x. X is equal to 0.1, x is equal to 0.2, all the way till x is equal to 0.5. So there are 5 experimental values of x at which the y values are given to be this respectively. So when x is equal to 0.1, f is 0.1125. And when x is equal to 0.2, f of x is 0.2227. So we have 5 samples, and therefore I can choose n is equal to 5. So when n is equal to 5, I goes from 1 to 5. So the highest power of x will be x to the power of 5 minus 1 will be x to the power of 4. So we are going to go for a fourth order polynomial, which is called a quartic polynomial. And a fourth order polynomial has 5 parameters. So 5 samples, 5 parameters, that will give us a perfect fit. That will be a good interpolating polynomial, because the perfect fit polynomial will pass through all the data points exactly. So now the error at xk, k going from 1 to 5, and ai's, right? I is equal to 1, 2, 3, 4, 5. So there are 5 parameters. So the error at each experimental point, and the error is also a function of the parameters that are yet to be determined. That error is nothing but f value, the true value of the function at those points, minus the value provided by our polynomial. And because this is a perfect polynomial, because the number of parameters equals the number of data points, you're going to get the errors to be equal to 0. So we have f of xk is equal to Pn minus 1 xk. And we know Pn minus 1 is nothing but summation ai x to the power of I minus 1 as I goes from 1 to n in this case. We have n is equal to 5, of course. This should lead to what you see here. Now, we have set up this problem many times in the past. Our polynomial is a1 plus a2x plus a3 x squared plus a4 x to the power of 3 plus a5 x to the power of 4. This is the quartic polynomial with 5 parameters. So to get a1, we should have a column of 1s. To get a2, you should have a column of x. To get a3, you must have a column of the squares of x. And to get a4, we should need a column of the cubes of x. To get a5, you should have a column of the fourth powers of the x measurements. So this is what we have. Here we are calling this matrix as P. Previously we called it as V, and before that we called it as X. Alright, so it doesn't matter. You can call it the big X matrix, or you can call it the V matrix, or in this case you have used the symbol P. So this kind of a matrix is called Van der Monde matrix, just a name for that. I use the values of x1, x2, x3, x4 and x5 that's available in this particular data set. X1 is 0.1, x2 is 0.2 and so on. So you can get this to be the column of x measurements. And when you square each of these elements, you will get this column. When you cube each of these elements, you will get this column. When you take these elements to the power of 4, you will get this column. So the V matrix or the P matrix or the big X matrix is full. Now A is A1, A2, A3, A4, A5. So A vector is this, and this is what needs to be determined. And F is this basically, expressed as a column vector. Here it's given as a row vector. We have to express it in the form of a column vector. So we have this P matrix, you have this unknown A vector, you have this known F vector. And therefore, you can find out A as P backslash F or other equivalent operations. In fact, you can use polyfit, or you can go to the curve fitting tool and fit a polynomial to it. You will get the answer that is given here. So I just said using MATLAB, we can get this A1, A2, A3, A4, A5, and we can write it like this. So you can use polyfit, or you can use curve fit, or you can use least squares kind of an idea to solve this problem. You should get these to be the answers. You should get this P4 polynomial, whichever path you choose. Now, if you sketch this polynomial and the experimental data is given as circles, the polynomial is given as the blue line. So if you are looking at it between 0 to 0.5, this is x, right, on the horizontal axis. So you are showing it over the range for which you have experimental values, right, from x is equal to 0.1 to x is equal to 0.5. That was the experimental range. And when you plot the experimental data as red circles and the polynomial fit the values that the polynomial provides for those x values in the range 0.1 to 0.5, you see a very, very good fit. Particularly, the polynomial passes through the center of each of those data points. That means it's a perfect fit for the 5 data points because you have utilized all the 5 degrees of freedom. So no surprises there. But then what you do is you now try to look at the behavior of the polynomial and the behavior of the function beyond the range of experimental data. So the experimental data range stops right here at x is equal to 0.5. Now you're looking at values of x up till 2. So what you see as the red dash curve there is the true function. This is the error function from which that data was generated. The f data was generated using the error function. So the true function is the error function, which shows a saturation behavior like what you see there. The red dashed line, it kind of goes up, and then it flattens out. But you can see the polynomial fit, which is shown by the blue continuous line there. You can see that it shows deviations, right? In this range, there is no deviation. But as you go here, you see some small deviations. And here you see significant deviations. That is to be expected because you are extrapolating the polynomial. So it shows some rather interesting behavior beyond the experimental data range. And interestingly, this polynomial may not saturate at 1, whereas the true function saturates at 1. So this kind of an interpolating polynomial is best used for what it was intended for interpolation purposes or for very minor extrapolations. If you extrapolate it too much, the errors can be large and sometimes disastrous. What practitioners have found is our choice of basis functions is okay for toy problems, but when you're doing practical problems, this choice of basis functions 1x, x squared, x cubed, etc. is not good. The matrix can become ill-conditioned. So if you look at the condition number of this matrix, it might be poor. That means it may be a large value for the condition number, and condition value anything bigger than 1 or significantly bigger than 1 is problematic. So even if you go for a sixth order polynomial, etc., what happens is this P matrix can become ill-conditioned. That means inversion of the P matrix will not be accurate, which means your parameter estimates, the parameter vector A, will be computed incorrectly or will have very large uncertainties about it. So this choice of basis functions is not good. So what practitioners have done is they have found that other polynomials can serve as basis functions. For example, the Chebyshev polynomials denoted by the symbol t. So t naught, Chebyshev polynomial of 0th order is 1. Chebyshev polynomial of first order is x. So till now there is no difference between our usual basis function and the Chebyshev polynomials. But for the second order Chebyshev polynomial, the polynomial is 2x squared minus 1 and not x squared. So already there is a difference. And this is called a recurrence relationship. So you can get the higher order Chebyshev polynomials using this recurrence relationship. So if you know the first two Chebyshev polynomials, you can construct the third, fourth, fifth, etc. So T2 of x using this recurrence relationship, this is called recurrence relationship. And I'm sure you would have looked at recurrence relationship for Chebyshev polynomials, for Legendre polynomials, for Laguerre polynomials, etc. in a course where you study differential equations, Fourier series, and those kinds of courses. So I'm not going to go into these in detail here, but just to jog your memory, I can use this recurrence relationship to find out T2 of x. That means I've substituted n is equal to 1. So when n is equal to 1, T2 of x is going to be 2x times T1 of x minus T0 of x, because when n is equal to 1, this is 2, so 2, and when n is equal to 1, this is T1, and when n is equal to 1, this is T0. And we know T1 of x is x, so 2x multiplied by x is going to give you 2x squared minus T0 of x is 1. So T2 of x is going to be 2x squared minus 1, which is what we wrote here. If you want T3 of x, that means n is equal to 2. So you go 2x multiplied by T2 of x minus T1 of x. That would be the expression for T3 of x. So that will give you 2x times T2 of x, we just wrote it as 2x squared minus 1, minus T1 of x is x. So this is going to be 4x cubed minus 3x. That will be T3 of x. So instead of using x to the power of 0, x to the power of 1, x to the power of 2, etc. as your basis functions, you can use 1x, 2x squared minus 1, 4x cubed minus 3x, etc. as basis functions. And these are known to provide well-conditioned regression problems so that you can estimate the parameters AI appropriately. So in that case, right, f of x will be approximated as a1 t0 of x plus a2 t1 of x plus a3 t2 of x plus a4 t3 of x, etc. So again, all you need to do is to find out a1, a2, a3, a4 using the idea of least squares. Now, this is the last slide for this particular video lesson. And the problem is simple. I'm not going to discuss the answers for this. That's not my intention here. But I just want to provide you some options. So here we have saturation temperature versus pressure data taken from a thermodynamics table. And this is the temperature and this is the corresponding pressure. Now you are asked to express the pressure as a function of temperature so that you can do interpolation first, and if you have to do numerical differentiation or integration, you can always do it later. If you want to express P as a function of T, then given 4 data points, an obvious choice for an interpolating polynomial will be to find one polynomial of order 3. A polynomial of order 3 will have 4 parameters, and since you have 4 distinct data points, you can go up till P3 of t. So you take all the 4 data points, fit a third order polynomial to it, and since that polynomial will pass through all these 4 data points, it's called a global interpolating polynomial. Global because you have utilized all the data points. Interpolating because the polynomial is going to pass through all of them. So that can be one functional approximation to this data. The second possibility is you take these 3 points and for those 3 points fit a second order polynomial. Second order polynomial will have 3 parameters, and if you take these 3 data points, P2 will be a interpolating polynomial. It will pass perfectly through those 3 data points. So I can make a P2 for this, a second order polynomial for this, and then I can make a second order polynomial for these 3 data points. That will also be an interpolating polynomial. So now you have 2 polynomials, both of order 2. One is valid for this range and another is valid for this range of temperature. So one is valid from 220 Fahrenheit till 228 Fahrenheit. The other polynomial is valid from 224 Fahrenheit till 232 Fahrenheit. And then depending on your query point, you can use whichever polynomial you want. So here the polynomials are not global in nature. The polynomials are rather local. This polynomial is local to this region. This polynomial is local to this region. Of course, there is an overlap. You are asked to find out the value of P at t is equal to 222. You can use this polynomial to get that. If you are asked to find out the value of pressure at temperature is equal to 231 degrees Fahrenheit, then you can use this polynomial. If you are asked to find out the value of pressure at t is equal to 227, then you can use this polynomial or both, take an average and then give out the answer. So that is a second choice. And such multiple models are becoming very common in the chemical process industry because there is no single model, there is no global model that will work very well for the entire range of operation. So the idea is to have local models that serve like local specialists and work well for a certain region. Then there is a conflict between one model and many models. Of course, we understand local models will do very well as far as their local domain is concerned. So it is great. But if you have too many of them, then that can itself become a problem because plant operators and engineers do not like to have too many models because maintaining them can be a problem. So a global model can be quite approximate. It is like a generalist that can work reasonably well but not exceedingly well. The local models can be specialists in that they can work very well over a narrow range. But if you have too many models, then it becomes difficult to maintain each of them. Constructing models in the process industry is not that difficult, but making sure they work well over several months and years, that is going to be a problem. So we must monitor the performance of models and recalibrate them whenever needed. So if you have too many models, that can become a problem. So this is a philosophical issue. The third option that I want to highlight is that you can fit a second order polynomial to all the four data points together. But this will not be an interpolating polynomial because a second order polynomial will have three parameters and you have 4 points here. So a second order polynomial will not pass through all the four data points perfectly. It will pass through it in a least square sense. So which strategy out of these three listed here you want to adopt is your choice. In fact, you could think of other possibilities as well. For example, I can use these two data points, fit a linear model for that. So I can use a linear polynomial. Then I can choose points 2 and 3 and I can fit a linear polynomial to it. And then I can take samples 3 and 4. I can make a linear polynomial for that range. So I can have three linear models. This is called piecewise linear model. So between any two data points, I connect them by a line. And that line serves as an approximation for points in between. So there are many possibilities, some of which I've highlighted here. So when you solve a practical problem, it is up to you, and you will see as a plant engineer, you will see which strategy works well, and then you will deploy that in your process. Thank you for your time.